New seismometer installations focus on detecting deep earthquakes and monitoring regions that require additional data for comprehensive geological assessment. The expansion of monitoring capabilities reflects scientific interest in understanding current seismic patterns through conventional geological frameworks rather than preparation for catastrophic events. The seismic patterns observed in 2025, while notable for their regional variations and timing correlations with magnetic changes, operate within the bounds of normal geological processes. However, these geological adjustments are occurring alongside atmospheric changes that present their own concerning patterns, climate chaos and atmospheric anomalies. Weather patterns recorded throughout 2025 show characteristics that meteorologists describe as unprecedented in recorded history. Temperature variations between different regions of the planet have reached extremes that don't follow seasonal patterns or gradual climate change trends. The Arctic has experienced temperature swings of over 40 degrees Fahrenheit within single weeks, while tropical regions have recorded heat indices that exceed normal measurement ranges. These temperature extremes appear suddenly and persist for weeks before shifting to equally extreme conditions in the opposite direction. Atmospheric circulation patterns have fundamentally changed from the stable systems that meteorologists used for weather prediction throughout the 20th century. The polar vortex has experienced disruptions in 2025 that sent cold air masses further south than typical patterns, though within documented ranges of Arctic outbreaks. NOAA data shows jet stream perturbations that create temperature inversions where some northern locations record higher temperatures than areas hundreds of miles closer to the equator. These circulation disruptions create feedback loops that amplify weather instability rather than allowing atmospheric systems to return to normal patterns. Jet stream behavior throughout 2025 demonstrates unprecedented undulations that meteorologists are working to understand through conventional atmospheric science. The jet streams, which are high-altitude air currents that normally flow in relatively stable west-to-east patterns, have developed extreme loops that persist for weeks instead of the few days that characterize normal jet stream variations in previous decades. The northern jet stream has created massive undulations that bring Arctic air into temperate regions while simultaneously pulling warm air into polar areas. These patterns correlate with known climate oscillations including the Arctic Oscillation and El Niño Southern Oscillation effects, though their intensity exceeds historical ranges. The relationship between atmospheric changes and other planetary systems has become increasingly apparent as multiple phenomena have intensified together since 2019. Research teams studying these connections have documented that atmospheric disturbances follow some geographic patterns similar to regions experiencing magnetic field changes, though the mechanisms linking these phenomena remain subjects of ongoing scientific investigation. Current atmospheric disruptions operate through conventional meteorological processes rather than direct electromagnetic control of weather systems. Climate system changes are accelerating beyond the gradual warming trends that scientists previously documented through anthropogenic greenhouse gas forcing. The Intergovernmental Panel on Climate Change identifies human activities as the primary driver of current climate change, with greenhouse gas concentrations reaching levels that create enhanced warming effects. Ocean circulation patterns that typically change over decades are now showing variations within shorter timeframes. The Atlantic meridional overturning circulation has weakened significantly since 2000 and shows signs of continued decline. Similar changes are occurring in Pacific Ocean currents that normally provide climate stability for billions of people. Historical climate patterns preserved in ice cores and sediment layers show atmospheric conditions similar to current observations during previous periods of rapid environmental change. These paleoclimate records indicate that rapid atmospheric transitions occurred in coordination with other planetary changes throughout Earth's history. The atmospheric signatures include sudden temperature shifts, altered precipitation patterns, and atmospheric composition changes that provide context for understanding current observations. Ice cores from Greenland show that previous periods of rapid climate change involved atmospheric instability that intensified over periods of 10 to 20 years before reaching peak intensity. Environmental stability indicators that meteorologists use to assess long-term climate trends show accelerating changes throughout 2025. Atmospheric pressure patterns have become increasingly variable, with high and low pressure systems developing intensities that challenge weather prediction models. Storm systems are generating wind speeds and pressure gradients that exceed historical ranges for many regions. Hurricane and typhoon seasons have extended beyond their normal timeframes, with tropical storms forming in regions and seasons where they occurred less frequently historically. These storms are also maintaining strength at latitudes where they typically weaken, indicating that atmospheric energy distribution has changed. Extreme weather events in 2025 show clustering patterns that suggest they're responding to common underlying atmospheric forces rather than random climate variations. Heat waves, flooding, drought, and severe storms are occurring simultaneously across different continents in ways that indicate planetary-scale atmospheric disruption. The synchronization of extreme events matches computer models of atmospheric behavior during periods of rapid climate system change. These models predict that enhanced greenhouse forcing combined with natural climate variability would create atmospheric instability that generates coordinated weather extremes across multiple regions simultaneously. Regional climate zones are shifting at rates that represent significant departures from historical patterns. Areas that maintain consistent climate characteristics for decades are experiencing temperature and precipitation changes that represent transitions toward different climate classifications. Desert regions are receiving unusual rainfall while traditionally wet areas are experiencing severe droughts. These shifts represent rapid transitions between climate states rather than gradual adaptations to changing conditions. The speed of these transitions suggests that atmospheric systems are approaching critical threshold points where small changes trigger large-scale reorganization. Atmospheric monitoring networks have detected pressure wave patterns that propagate through the atmosphere in ways that require further scientific investigation. These waves appear to correlate with geological activity and create pressure disturbances that affect weather patterns across large regions. The waves show characteristics that suggest they may represent coupling between Earth's interior dynamics and atmospheric systems that becomes more pronounced during periods of increased geological activity. Atmospheric scientists working with current data confirm that 2025's weather patterns represent significant departures from historical norms, indicating that Earth's climate system is undergoing rapid changes through both anthropogenic forcing and natural variability. These atmospheric changes are occurring alongside mounting evidence that similar rapid environmental transitions have occurred multiple times throughout human history, leaving traces that researchers are only beginning to understand. The Lost Civilizations Connection. Archaeological discoveries from 2020 through 2025 have uncovered evidence that challenges established timelines of human civilization. Teams working with ground-penetrating radar have identified massive stone structures buried beneath sediment layers in locations where mainstream archaeology previously found no evidence of advanced societies. These discoveries include precision-cut megalithic blocks, sophisticated drainage systems, and architectural foundations that demonstrate engineering knowledge that appears earlier in human history than previously documented. The structures show construction techniques that require advanced mathematics, astronomy, and metallurgy to accomplish. Excavations at sites in Turkey, Peru, and Indonesia have revealed technological capabilities that suggest human advancement occurred earlier than conventional archaeological timelines indicate. At Göbekli Tepe, researchers continue finding evidence that the site required coordinated labor from thousands of workers using tools and techniques that represent sophisticated organizational capabilities for societies existing 12,000 years ago. The site's construction demonstrates planning and execution that required substantial social coordination and technical knowledge. However, mainstream archaeology attributes these achievements to known cultures rather than evidence of Prediluvian advanced civilizations. The construction techniques found at ancient sites demonstrate knowledge that goes beyond basic building skills documented for their respective time periods. Engineers analyzing megalithic walls at various ancient sites have identified construction methods that create earthquake-resistant structures capable of surviving seismic events that would damage conventional buildings. The stones are cut and fitted using interlocking techniques that allow walls to flex during ground movement without collapsing. Similar earthquake-resistant construction appears at ancient sites across different continents, suggesting that builders understood the need to create structures that could survive geological instability. Archaeological evidence indicates ancient builders possessed detailed knowledge of geological stability and catastrophic risk assessment. The positioning of major archaeological sites follows specific geographic criteria that correspond to areas identified by modern geological analysis as relatively stable during seismic events. Megalithic sites are often concentrated in regions that sit on stable continental platforms, away from major fault lines, and at elevations that would provide protection from flooding. This geographic distribution suggests the builders understood which locations would survive natural disasters and chose their construction sites based on geological stability criteria. Stone monuments and carved reliefs at ancient sites contain astronomical alignments that track celestial cycles with mathematical precision. The Sphinx and pyramids at Giza align with stellar configurations that correspond to precession cycles, while similar astronomical alignments appear at Stonehenge, Angkor Wat, and sites throughout the Americas. These alignments required sophisticated astronomical knowledge and suggest the builders were tracking celestial patterns they considered important for their civilizations. The mathematical precision needed to create these alignments indicates the builders possessed advanced understanding of orbital mechanics and long-term astronomical cycles. Carved symbols and artwork at megalithic sites contain representations that appear to document catastrophic events and survival strategies. Petroglyphs found at sites worldwide show symbols representing floods, geological movement, and astronomical events. The symbols appear across different continents in cultures that had limited known contact with each other, suggesting they represent shared knowledge about natural catastrophes. Some symbols show representations of the Earth experiencing dramatic changes, floods covering large areas, and groups of people seeking shelter in elevated locations. The consistency of these symbols indicates they may represent attempts to preserve knowledge about natural disaster cycles for future generations. Claims about multiple successive advanced civilizations with specific catastrophe-proof designs remain disputed within archaeological circles. While some researchers propose theories about lost civilizations like Atlantis, conclusive evidence for such societies remains elusive. The archaeological record shows evidence of sophisticated ancient cultures, but mainstream archaeology attributes these achievements to known historical societies rather than evidence of cyclical destruction and rebuilding by advanced Prediluvian civilizations. The interpretation of ancient sites as evidence of lost advanced civilizations requires assumptions that extend beyond current archaeological consensus. Underground installations discovered through ground-penetrating radar suggest ancient civilizations built extensive subterranean complexes that could provide protection during surface disasters. These installations show evidence of advanced planning and include features designed to support populations during extended periods of isolation from surface conditions. The complexes include ventilation systems, water supplies, and storage areas that demonstrate sophisticated engineering capabilities. However, mainstream archaeology dates these structures within established historical timelines rather than as evidence of prehistoric advanced civilizations. Archaeological sites show evidence of knowledge preservation systems designed to protect information through natural disasters. Stone chambers at various sites are constructed to protect interior spaces from floods, earthquakes, and other environmental threats while preserving carved information on interior walls. The chambers are built using materials and techniques that maintain structural integrity over extended periods. These preservation systems suggest ancient civilizations developed systematic approaches to protecting important cultural and technical knowledge through periods of environmental instability. Advanced manufacturing techniques found at ancient sites indicate technological capabilities that appear sporadically throughout the archaeological record. Archaeological evidence shows that ancient civilizations produced sophisticated tools and worked with materials that require advanced processing techniques. However, these capabilities appear at different times and locations in ways that suggest independent development rather than inheritance from previous advanced civilizations. The pattern of technological advancement shows normal cultural development rather than evidence of cyclical destruction and rebuilding. Construction projects at ancient sites show evidence of multiple building phases separated by periods of abandonment and reconstruction. Carbon dating reveals that major sites were built, abandoned, then rebuilt by later civilizations using different construction techniques. This pattern reflects normal cultural transitions, population movements, and technological development rather than evidence of catastrophic destruction followed by rebuilding. The rebuilding efforts show that later civilizations found and studied the remains of previous societies, incorporating useful knowledge into new construction projects. Archaeological evidence demonstrates that ancient civilizations possessed sophisticated knowledge and capabilities that challenge conventional timelines of human development. However, The interpretation of this evidence as proof of cyclical catastrophic destruction remains outside mainstream archaeological consensus. The mounting evidence of ancient sophistication raises questions about human technological development that researchers continue investigating through conventional archaeological methods. These questions become particularly relevant when considering how dependent modern civilization has become on technological systems that require stable environmental conditions to function properly. Modern technology's vulnerability. Critical infrastructure systems across the globe face unprecedented risks from the accelerating magnetic field changes documented throughout 2025. Our electrical power grids depend on stable magnetic conditions because transformers and transmission lines are sensitive to magnetic field fluctuations. When the magnetic field experiences rapid changes, it induces electrical currents in power lines that can overload transformers and cause widespread blackouts. The 1989 geomagnetic storm that knocked out power across Quebec for 9 hours demonstrates how magnetic disturbances can cripple electrical systems. However, magnetic pole reversals occur gradually over thousands of years according to paleomagnetic records, meaning power grids face risks from space weather events like solar storms rather than sudden magnetic field collapse. Satellite networks that provide communication, navigation, and internet services are extremely vulnerable to magnetic field disruption and space weather effects. Satellites operate outside Earth's protective atmosphere where they rely on the magnetic field to deflect harmful radiation from space. As the magnetic field weakens, satellites experience increased radiation exposure that damages their electronic components and shortens their operational lifespans. The GPS satellite constellation has already required more frequent maintenance and replacement due to radiation damage from weakened magnetic protection. NASA research confirms that while magnetic reversals happen gradually, the weakening magnetic field during the transition period increases satellite vulnerability to solar particle events and cosmic radiation. Navigation systems used by aircraft, ships, and ground vehicles all rely on magnetic field measurements for accurate positioning. Airplane autopilot systems, marine compasses, and smartphone navigation apps require precise magnetic declination data to function correctly. As magnetic field changes accelerate, these systems are producing increasingly inaccurate readings that create safety hazards for transportation. Commercial aviation has already implemented new procedures requiring pilots to verify magnetic compass readings against GPS coordinates because magnetic navigation is becoming unreliable. The accelerating magnetic pole drift documented in 2025 means navigation systems require constant recalibration to maintain accuracy. Computer systems and electronic devices face potential failure during severe geomagnetic storms because they're designed to operate within specific electromagnetic parameters. The integrated circuits that power everything from smartphones to industrial control systems are sensitive to electromagnetic interference. Strong magnetic field fluctuations can induce electrical currents in electronic circuits that cause temporary malfunctions or permanent damage to sensitive components. Modern electronics lack the hardening necessary to survive severe electromagnetic effects, though the gradual nature of magnetic reversals provides time for technological adaptation. Banking and financial systems that rely on electronic transactions and digital records would face significant disruption during severe space weather events. Credit card systems, ATM networks, and stock market trading platforms all depend on satellite communications and computer networks that could fail during electromagnetic storms. The global economy operates on electronic transfers and digital record keeping that remain vulnerable to electromagnetic disruption. NOAA and FEMA have established protocols for geomagnetic storm preparedness that include backup systems for critical financial infrastructure. Food distribution systems in developed countries depend on complex logistics networks that coordinate transportation, refrigeration, and inventory management through electronic systems. Trucks delivering food to grocery stores rely on GPS navigation and electronic communication systems to operate efficiently. Refrigeration systems that preserve food during transport and storage require electrical power that could be disrupted by geomagnetic effects on power grids. Modern agriculture uses computerized equipment for planting, harvesting, and processing crops that would face challenges during severe electromagnetic events. Medical systems and hospitals operate life support equipment, diagnostic machines, and pharmaceutical manufacturing that all require stable electrical power and electromagnetic conditions. Patients dependent on electronic medical devices like pacemakers, insulin pumps, and dialysis machines would face serious risks during severe geomagnetic storms. Hospital backup generators and medical equipment aren't designed to handle intense electromagnetic interference. Emergency preparedness protocols now include provisions for protecting critical medical equipment during space weather events. Water treatment and sewage systems in urban areas rely on electric pumps, computerized monitoring, and automated control systems that could fail during electromagnetic disruption. Cities pump water from distant sources using electrical systems and treat sewage through processes that require constant electrical power. Urban populations that depend on these centralized systems would lose access to clean water and sanitation during extended power outages. Emergency management agencies have developed contingency plans for maintaining essential services during infrastructure disruptions. Transportation networks including air traffic control, railroad signaling, and highway management systems all depend on electronic communication and navigation that electromagnetic storms could disrupt. Air travel would face significant challenges without radar systems and electronic navigation aids that keep aircraft safely separated. Rail transportation relies on computerized signaling systems that prevent collisions and coordinate train movements across networks. Highway systems use electronic traffic control and emergency communication systems that remain vulnerable to electromagnetic effects. Manufacturing and industrial processes use computerized control systems, robotic assembly lines, and electronic monitoring that could shut down during severe geomagnetic events. Chemical plants, oil refineries, and nuclear power facilities require constant electronic monitoring and automated safety systems to operate safely. These industrial facilities have implemented backup systems and electromagnetic hardening measures for critical operations. The industrial infrastructure that supports modern civilization has developed resilience measures for space weather events. Government preparations for electromagnetic disruption include established NOAA and FEMA protocols for geomagnetic storm preparedness rather than classified extinction-level threat programs. Military installations have implemented electromagnetic hardening measures for essential communication and defense systems, while civilian infrastructure continues developing protective measures. Emergency management agencies have developed contingency plans for widespread power outages and communication failures based on documented space weather risks. Scientific institutions have studied the cascading failure effects that severe electromagnetic events could create across interconnected technological systems. Computer models show that failure of satellite communications could trigger failures in power grids, which would cause failures in water systems, transportation networks, and financial systems in sequence. The interdependence of modern technological systems means that failure of major components could cause failures throughout infrastructure networks. However, the gradual nature of magnetic reversals provides time for adaptation and system hardening. The mounting evidence of accelerating magnetic field changes, combined with increasing technological dependence, has prompted researchers to examine whether current conditions might indicate approaching critical thresholds. While electromagnetic risks operate through conventional space weather processes rather than catastrophic scenarios, the patterns emerging in 2025 suggest that understanding the timing of these changes. The timeline question.